You 100% need your periodic table. All right, do you guys want me to write on a dark background with light writing?
That's aesthetic.
Yeah?
Yeah.
Okay.
Can we turn the lights off?
Turn off the lights? No, I feel like that'd be dark. I feel like that'd be weird. Okay. Let's, does that look good? Do you like that? Yeah? I don't feel like blue's not going to show up very well.
Blue won't show up.
I feel like it's not going to show up very well. Okay. So we are moving to chapter 10 in the book. What? Yeah, we're going to take some notes. Pretty easy today, though. So chapter 10, I like to call nuclear chemistry. Chapter 10 is nuclear chemistry. Nuclear chemistry. So we're going to start out with radioactivity. Radioactivity. So, what would you consider? What is it? What does that mean? What does it mean if something is radioactive?
It's dangerous
Why?
because it can kill you.
Ted? You're close. It's elements with unstable, the key word is nucleus or nuclei. With unstable, Nuclei, nuclei is the plural of nucleus. So, if they're unstable, what do they want to do? They want to become what? Stable. Yeah. So, to become stable, to become more stable, they go through what is called radioactive decay. Radioactive decay. So radioactive decay is our idea for the day. So there are essentially 4 types of radioactive decay we're going to talk about. So we're going to talk about each of these 4 types. There's 4 types. There are 4 types that we're going to be talking about. So, type number 1 is called alpha. Why is that funny?
You should ask.
Yeah, why is that funny?
Yeah.
Corey?
I don't know why. Are you an alpha?
I'm not an alpha.
Okay. So, alpha is symbolized by, how does this look? Kind of like this. All right, so that's alpha, like a fish. And this is essentially a proton, all right, or kind of the nucleus of a helium atom. So, helium is 4,2He. 4,2He. The number on the top is what? What's the number on the top? For helium? No. Look at your periodic table. What is the number on the top for helium? No.
At the top is 2.
No. This number. 4 is what? That's the mass number. Right? So the number on the top is the mass number. Because you guys would agree that is the rounded atomic mass for helium. Yes? Okay. And what is the number on the bottom here? This 2. The number on the bottom is the what? The 2 is the what? Huh?
Atomic number.
Yeah, that's the atomic number, right? Helium has the atomic number 2? Yes?
Yes.
Okay. This is the atomic number. So that's what we're going to be looking at. It's always going to be set up like that. Number on the top is atomic mass. Number on the bottom is atomic number. Alpha radiation is not very dangerous. So this is not, so while it's the alpha, it's not very dangerous. Anybody have a guess of why? Yeah. True. Why? It's heavy. All right? This is heavy. So it's too heavy. That's why it's not very dangerous. So an alpha particle essentially can't even go through, like your skin, can't even go through a piece of paper. Yes?
So like X-rays have radiation in it.
Yes.
Why?
Well, that's light. We're talking about particles here.
Is it different?
So you're talking about a different wavelength of light. So X-rays are X-rays. So like we're going to talk about the electromagnetic spectrum, okay? We're talking about individual particles right now. We'll talk about X-rays later.
That's like, okay.
So that's like a different wavelength of light. Okay. So that is an alpha particle. The second type of radiation. Anybody have a guess of what it would be? Anyone know Greek?
Beta.
Beta. Yeah. It is beta. So a beta, the symbol for beta is kind of like a big B with a tail. I don't know how to write a beta symbol. I don't know. Okay. Something like that. What? Kind of. Yeah. A beta particle is this. 0, -1, E. I'm going to put a box around these particles so we don't lose track of them. Anybody have a guess? So this is a proton, essentially. Anyone have a guess what this is?
Electron.
It's an electron, right? Because an electron has what mass, essentially? 0, right? Does an electron have any protons? No. And what is an electron's charge? -1. So this is an electron. So this is a beta particle. These are essentially fast-moving electrons. So these are fast-moving electrons. Are fast-moving electrons. And these can penetrate paper. I know. So these can go, yes, these are stronger than the alphas. So the beta in chemistry, nuclear chemistry, is actually stronger than the alpha. So these can penetrate paper. Third type. Third type is gamma. Third type is gamma. And the symbol for gamma is kind of like that broken Y type thing, right? So it's actually Y, 0, 0. So this is the gamma particle. There's no mass. There's no charge. It's what?
0, 0. What's the letter?
Gamma. So this is the particle for gamma. So the gamma particle doesn't actually change the mass or the number of protons. What is it? It's an electromagnetic wave. So this is what Corey was talking about. So the gamma particle, these are electromagnetic waves. Just like X-rays. X-rays are also electromagnetic waves. Okay? These are electromagnetic waves of energy. These can go through the skin. These can penetrate skin. And a lot of gamma particles are coming from space, from the sun, right? The sun can let off gamma particles. They're coming from space. What? Well, that's UV. All right? So ultraviolet is another wavelength of light. So Corey is like a couple chapters ahead. That's fine. Okay? He's thinking different wavelengths. But gamma particles are the highest energy light. So gamma particles are more dangerous than X-rays. Nadia.
So, you said that the gamma particles come from the sun. Does that mean that they help in causing sunburns and stuff?
They do what?
They help cause sunburns? Since they...
I mean, they don't. The gamma particles are more going to give you cancer. They're gonna mess with your DNA in your skin. So they're gonna go through your skin and mess with your DNA. The ultraviolet light is going to give you the sunburn. So UV light is a shorter wavelength than gamma. Shorter wavelength than gamma. So that's gamma. This can penetrate skin, but that is not the most dangerous.
Oh my god.
That is not the most dangerous.
DUH_Z.
The most dangerous. Anybody know? Ted, you seem to know this. No?
There's Alex in orchestra.
The most dangerous is
No.
neutron.
You gotta.
The most dangerous is neutron radiation. Neutron radiation. The symbol for this is 10N.
They come up with a name for this one.
How? Because it's a neutron,
They
essentially.
could have called it like something else.
I know, alpha, beta, gamma, neutron.
Yeah, like beta is.
Should have called it like Nana.
Beta's pretty cool. Beta
I actually don't think
like
Nana's a thing,
electron.
but I know. So, but a neutron is just a neutron. This is the most dangerous. This is the most dangerous. Here's how you know. It can go through 15 centimeters of lead. So that particle can penetrate a lot. 15 centimeters of lead. And we know there's 2.54 centimeters in an inch, right? So we're talking like 7 inches of lead. That's how far a beta particle can go through. And what do they put on you at the dentist?
I don't know.
A lead cape, right?
That's not 15 inches.
It's not, but they're also not shooting neutrons at you. All right? They're shooting X-rays at you, so it can't go through as much. So, and then make sure you guys get the neck part too, right? The thyroid part. Okay, that's important.
I don't.
Your dentist should give you like the neck cover as well when you get an X-ray.
They don't care.
Okay,
What
well,
if they don't? Should we
They
keep
can
it
be like
like
a rope.
when like it's not good for your.
I'll be like, my science says you're in danger. And like,
I would ask him why you don't have the thyroid part of it. I'm just saying. When you guys go to the dentist, you guys, the cape should go here, and then there's also like a part that should go around your neck.
What?
Is it?
I feel like it's one
Maybe
thing.
we're just.
Maybe you're not paying attention.
Lawsuit, yeah.
Yeah.
When you get X-rays,
Maybe we're just.
oh,
Let's go. Let's go.
I don't know. So, we have these 4 particles. We have these 4 particles. What are we going to do with them? All right? I'm going to show you. So, I could say, show the alpha decay. All right? So, show the alpha decay of thorium dash 234. Show the alpha decay of thorium dash 234. So that means that thorium is going to decay and give off a particle, a beta particle. So do you have your periodic table out? You definitely need it. Because now we're going to be down here in these heavier particles. Maybe down here, these are heavier particles. So these are going to be ones that you know. So thorium is what symbol?
TH.
TH. So TH, what is thorium's mass number?
230.
What?
What? No, sorry, 90.
No?
Dude, what are you doing?
230.
Yes, 232. Thorium is 232. Yes.
Wrong, Avery.
232, yes. So 232. What is thorium's atomic number? 90. It's 90. So that's the thorium. It's going to decay into something more stable. The first thing, what's it going to give off? It's going to give off what type of particle? Alpha particle, which is what? 4, 2, He. So that's the particle it gives off as it becomes more stable. And it turns into something new. What is? Oh, wait. Pause. Pause. What is this 234 in the name? That's thorium's what? Mass number. So what should this number on top be? 234. This is a different isotope of thorium. Fix that. 234. Because we know that the mass number doesn't have to match the periodic table. Yes?
Yeah.
Okay. I'm glad I caught that. So, Now you just have to subtract. If you write it like this, you literally just subtract. What is 234 minus 4?
230.
So this gives me 230. What is 90 minus 2? 88. What has an atomic number 88 on your periodic table?
HG.
No,
Grams?
that's 80. What?
Radium.
Radium. Ra.
Ra, radium. So, when you are looking at the beta decay of thorium, thorium gives off a beta particle and turns into radium. That's beta decay. That's an alpha decay, sorry. So you literally just subtract across. That's all you have to do. It's super easy. Or sometimes they'll give you this and you'll have to like figure out what this was. Really easy. What if I said, show the beta decay, show the beta decay of radium 230. So let's take this radium. So we're going to decay that now again. So we're going to decay what I just got. So show the beta decay of radium 230 88. So I'm going to have 230 88 Ra. What particle is that going to shoot off?
Oh, negative.
It's going to shoot off a beta particle, which is an electron, right? Which is what? 0, 0, negative 1, E. That's my beta particle, right? Yes?
Yeah.
Okay.
That's gonna equal.
Plus, okay, what is 230 minus 0? 230. What is 88 minus negative 1? 89. You got it. So, what has an atomic number of 89? Actinium, yes. So that is AC. That is AC. So this first section is just alpha and beta decay. We're going to talk about those other ones later as we move on throughout the week. Okay? So if I gave you this, let's say I gave you like, I don't know, 222, 86 Rn, and that gives me 220, 84. Oh, wait. I gotta make something that actually works. Sorry. 220. Let's do something better. These are hard to come up with off the top of your head. Okay, let's do 240, 94 PU gives me something plus 238, 92 U. Could you identify? Oh, wow, that's still wrong. That would have to be 234. No. Wow. Guys, my brain is not warmed up. 236. That's not 236. There we go. That gives you 236, 92 uranium. Could you identify the type of decay that happened here?
Yeah.
What type of decay happened here?
Alpha.
Alpha, right? Because 230 minus what gives me 236? 4. 94 minus what gives me 92? 2, which is an alpha particle, 42He. Cool? Your homework is a piece of paper you picked up on the way in. You should probably finish that, I think, before you'll leave. Get it done.
Where's the